Do you feel the vibes?
Hey guys, I know you did 7.1 yesterday, and today you are going to learn 7.2. Exciting! Okay, let's go ahead and get started. So in 7.2, we are going to solve exponential equations and inequalities. So let's start with the first property. The property says b of x equals b of y if and only if x is equal to y. If you notice, this was actually one of the challenge problems in the last chapter, and there was a bonus question like this on your test. Remember what we said before? We said this is a, it's if and only if, it's an if-then statement. So basically, if this, then this, and it also goes in the opposite direction, right? Okay, so basically what this is telling us to do is to make it so that the bases on both sides of the equation are the same. All right, so take a look at this one here. I have a base of 3 and a base of 9. Okay, we all know that those two are related. The 3 is the simplest base, so there isn't much I can do with that. Equal to. Now the 9 here, right, I can actually rewrite that as 3 to the power of something. Remember, I need to make these two bases the same. So I can make the 9 3 squared, right? This will be to the power of 4. So this is actually 3 to the power of 8. So now what I can do is the following. I can set the exponents equal to each other. So I say, okay, x plus 3 is equal to 8, x is equal to 5, and that's my answer. All right, let's do the same thing over here. I have 2 to the 5x, 4 to the 2x plus 1, minus 1. All right, 2 to the 5x is, a done deal. But this 4 can be written as 2 squared to the power of 2x minus 1. Since the bases are the same, I can set the exponents equal to each other. So 5x is equal to 4x minus 2. I distribute. Subtract 4x. X is equal to negative 2. Okay, let's move on here. All right, so in the case of this one, I have 1 over 5 and 5. Okay, definitely there is a common base of 5 there, but they both need to be worked with, right? So the 1 over 5 can be written as 5 to the minus 1, right? To the power of x minus 5. Equal to, this can be written as 5 squared to the power of 3x minus 2. So now, remember, like we distribute this, right? So negative x plus 5 is equal to 6x minus 4. I think I'm going to add x to both sides here. So 5 is equal to 7x minus 4. 9 is equal to 7x. And finally, x is equal to 9 over 7. Okay. This one. I have a root. We all know a root can be written as 3 to the 1 over 2 is equal to 3 to the power of negative 3x. Oh my gosh, same base. I can set the exponents equal to each other. 1/2 is negative 3x. Divide by negative 3, that's the same as multiplying by negative 1 over 3. So x is negative 1 over 6, and there we have it. Okay. So what if you have inequalities instead of exponents? Well, it doesn't change much, right? So b to the x is greater than b to the y if and only if x is greater than y. So it's really the same thing. And with a less than sign, it's the same thing. So honestly, nothing changes except instead of the equal sign, you're going to put the inequality. So here, I have 2 to the power x plus 2 greater than this one. Okay, so the 2 is not something I can work with. Greater than. Okay, 32. Remember, 32 is 2 to the 5. But if it's 1 over 32, then it's 2 to the negative 5. So x plus 2 is greater than negative 5. X is greater than negative 7, and that's it. There you have it. Now, let's pause a minute. In the case of exponential functions, remember the domain is always all real numbers. So there is not, it is not necessary to, check, right? Because you don't have a domain restriction. Okay, this one, 5 to the 3 minus 2x less than or equal to, okay, 625. What if you don't know what 625 is? Well, let's see. If you divide by 5, you get 125. If you divide by 5, you get 25. 5 and 5. So you can see 1, 2, 3, 4, right? So 625 is 5 to the power of 4. 1 over 625, 5 to the power of, that's right, I can hear you, negative 4. Okay, so now set the exponents equal to each other. Subtract 3 from both sides. Negative 2x less than or equal to negative 7. Now, when I divide by negative 2, remember, I have to switch the inequality so I get greater than negative 7 over 2. Sorry. I divide by negative, so this is greater than or equal to positive 7 over 2. Okay? All right, fabulous. Okay. Well, we can always solve equations, but can we write exponential functions? Of course we can. All right, so to write an exponential function, you have to have some information given. And you're going to substitute that information into this equation that you learned before. Okay, so you remember, when we had to write, an equation for a parabola, right? It was y equals a, x plus h squared plus k, and we would put in all the numbers and get a. It's a similar situation. This is the general form. We're going to put in the information we have, and we're going to solve for any constants. Okay, so let's see what these a and b and so on stand for. A is the y-intercept. Okay, and then you're going to have some coordinate point x comma y. Now, when you have application problems, word problems, not usually, a is always the initial amount and y is the amount after some time, right? So y-intercept or initial amount, those are both the same thing and they are both the values of a. So you plug everything in and you solve for b, and then you have to substitute a and b back into the main equation. All right, so let's take a look here. It says to write an exponential function for the graph. That passes through the given points. Okay, so take a look at what you have. You have 0, 6.4, 3, and 100. Now, this 0, 6.4 is no ordinary coordinate point. This is, when it's x equals 0, this is the y-intercept, right? So since this is the y-intercept, this value 6.4 is your A, right? That is the y-intercept, and that is the initial amount, okay? And then these two, the other coordinate point, can be taken as x and y. Right, so what was our equation? Y equals a b to the x. So remember, we first have to look for the y-intercept, which is this. And then the other one is going to be x and y. All right, so let's go ahead and plug this in. So y is equal to 100 is equal to a, which is 6.4. B, that's what we're solving for, to the power of x, which is 3. Okay, so there we have it. Now let's solve for b. Divide by 6.4, divide by 6.4. So I have 100 over 6.4 is equal to b cubed. Now, take the cube root, take the cube root. So b is equal to, well, we're going to plug it into our calculator, right? So we're going to take the cube root of what? 100 over 6.4. Do you notice how I didn't put it in before and I didn't round? I'm just putting it all in one shot. That's what I want you to do. So this is equal to 2.5. B is equal to 2.5. Next, substitute A and B back into the main equation. Leave x and y as variables. So let's see. Y equals a b to the x. Y equals a 6.4 times b to the power of x. And this is your equation, right? If y and x aren't in the equation as y and x, as the variables, then it's not going to be an equation, right? Remember, for an equation, you need an x, you need a y. So there you have it. Okay, why don't we do another one? So remember, we're always going to first look for that initial value and then a final value and plug it in. So Krista starts an experiment with 7,500 bacteria cells. After 4 hours, there are 23,000 cells. All right, so do you see how here we have an initial amount? That's your A. And then after 4 hours, you have 23,000 cells. So let's see if we can write coordinates for this. The initial value is 7,500. That means when t equals 0, the value is 7,500. And then when t equals 4, the value is 23,000. Okay, here you have to be careful about your commas, right? Because you have a comma for the coordinate, you have a comma for the placeholder. I trust you to keep those in check. Okay, so write an exponential function that could be used to model the number of bacteria x hours after if the number of bacteria changes at the same rate. Okay, our magic equation is y equals a times b to the x. Right. Y is the final amount, 23,000, is equal to a is the initial amount times b to the power of x, which is 4. Right? Okay, now I can divide these. All right, so look, if you have zeros on both sides of the equation, remember you can cancel out equal number of zeros. So what I have now, if I divide by 75, 230 over 75 is b to the 4. Take a fourth root, take a fourth root. We're going to plug this into our calculator. B is going to be the fourth root of 230 over 75, right? This number. Let's round to 3 decimal places, so it's 1.323. All right, let me write the equation. Y equals the initial value, 7,500, times b to the power of x. Okay? All right. How many bacterial cells can be expected in the sample after 12 hours? Now we have a new t, or in this case, x value. So let's go ahead and plug it in. Now, this is going to be y of 12, right? We can do function notation, is equal to 7,500, 1.323 to the power of 12. Now, we are not going to round this in the calculation. We're going to do 7,500 times the answer, press answer, to the power of 12, right? So we get, how much is it? 216,302.2. So that's y of 12. So that will be about 216,302 bacteria cells. Please don't automatically always round up. Just round mathematically to wherever it needs to be, up, down, wherever it needs to be. Okay. Now, before I move on, let's go back to part A for a minute. So you learned in the last lesson, 7.1, right, of the equation y equals a 1 plus r to the power of t. Remember that? So this is your 1 plus r, right? The rate is 0.323. 1 plus that, 1.323, is the growth factor, okay? All right. Another place we can use this is the compound interest formula. A compound interest is the following. You go to the bank, you deposit money in the bank, and suppose every month they're going to give you interest. So you have $100, they give you 1% interest, then you have 101. Then in the next month, they're going to give you 1% interest again, but not on the original amount, on the total amount. So now they give you 1% interest on the $101. And then, the next month, they give you 1% interest on the new amount, and the new amount, and the new amount. That's called compound interest. The formula for that is this. A equals P, 1 plus R over N to the power of NT. Look very carefully that N shows up twice. Okay, so N shows up twice. All right, now let's talk about what each of these things mean. If a principal P is invested, so this number is the principal, not principal like Miss Howard, but the principal, meaning how much money you had in your pocket when you went to the bank to open up your account. So that's your initial amount. R is the rate, obviously in decimal. T is time. A is the final amount. Basically, at the end of, whatever, when you get your statement, and, so you look and it's like, okay, how much money do I have in my account right now? That's A. Okay. What about N? N is the number of times you are paid per year, right? So let me say that again. N is the number of times you are paid per year. So let's talk about some examples of N. If you are paid interest yearly, then every year that happens one time, N equals 1. If you are paid monthly, that's 12 times a year, so N equals 12. Semi-annually, okay, like the Macy's semi-annual sale, that happens twice a year, so 2. Weekly, there are 52 weeks in a year, so 52. Bi-monthly, that's every 2 months, so 6 times a year. And then quarterly, right? 4 quarters in a year, so n equals 4. Okay, so let's take a look at this one. A sum of $8,000 is deposited into an account that pays 5% interest. Find the balance of the account 15 years later if the interest is compounded quarterly. Okay, so what do we have right now? We have a principal of $8,000. We have an account with an interest rate of 5%, that's 0.05. We want to find the balance A. We know that the time is it's 15 years. And if it's compounded quarterly, we know that n is equal to 4. And we're trying to find A. So, A is P 1 plus R over N to the NT. P is 8,000. 1 plus 0.05 over 4 to the power of 4 times 15. You're going to plug this in all in one shot. You're not going to break it up and round in the middle, right? You're talking about like dollars and cents. So you got to be like precise. So 8,000 times 1 plus 0.05 over 4, close to the power of 4 times 15. Enter. Before you go and you even look at the amount, look to see if your expression here is identical to the expression that you meant. Right, so it looks like we are getting, so much money here. So at the end of 15 years, we are going to have $16,857.45. So now look, this is money, right? You have to round it to 2 decimal places, but you got to round correctly, right? Can you imagine if the bank was off even by a penny? What would happen, right? Like that's embezzlement. Okay, that's what happened to Wells Fargo. Okay, and now they shut down. You don't want that to happen to you. Okay, all right. So let's talk about example 6. Okay. A savings account offers 0.8% interest compounded bi-monthly. If $150 is deposited in the account, what's the balance after 20 years? Okay, the rate is 0.8%, which is 0.008 in decimal. Okay, so A is going to be the initial amount, 1 plus 0.008 over 6 to the power of 6 times 20. You're going to plug all of that into your calculator, and you're going to end up with a whopping $176.01. Okay, lastly, in 1965, the population of Planet Algebra was about 6.248 million. By 1995, it had decreased to 4.987, right? They're going from Planet Algebra to like Planet, trigonometry. Write an exponential function in the form of y equals a times b to the x that could be used to model the planet's population, y, so the population is y, in millions from 1965 to 1995. Okay, so let's take a look at what we have here. In 1965, this is when this word problem started. This was the initial amount. So when t was 0 or x was 0, y is 6.248. Then in 1995, now 30 years have passed. So x is 30 and y is 4.987. You see that? Okay, so y equals a b to the x. Y is the final amount. So 4.987 is equal to a, the initial amount, 6.248, times b to the power of x, which is 30. Okay, fantastic. So why don't we divide by 6.248? That goes away, right? So now look at what I have. This is kind of cool. So 4.987 over 6.248 is equal to b to the 30th. Well, that's fine. Now I just do the 30th root and the 30th root. And when you go into your calculator, you're going to do it just that. The 30th root of this crazy number. Whew. All right. So 0.9925. Okay, so take a look at what it says here. It says to round b to the nearest 1,000. That is 3 decimal places, right? Okay, so when we write our equation, it's going to be y equals a times b, 0.993, to the power of x. Okay, next. Suppose the population continued to decrease at the same rate. Estimate the population in 2005. So in 2005, now 40 years have passed from the initial, right? So now x is equal to 40. So we want y of 40, 6.248, 0.993 to the power of 40. Okay, when you go here, this is my value of b, right? Okay, I'm going to show you guys something super, super cool right now. Let's go up here. So press up, enter. Do control variable above the 9. It gives you that arrow. Control variable. We're going to store this as some letter A, right? Just type in A. Enter. Now, A is just stored as that number. So look, if I just type in A, right there. If I type in 2A, 2 times that number. Okay, so now let's go back to our problem. What do I have here? 6.248 times A to the power of 40, right? Like you could have called it, whatever you want. You could have called it L, So it's going to be 6.248 times A to the power of 40. So if A has a value attached to it, when you type it into the equation, it's bold. That's how you know it has a value assigned to it. Okay, oops, enter, I pressed twice. And that's our value, okay? So it's 4.626. So I'm really going to expect everybody to do that, because when you do that, you can have like 15,000 people take any test and 15,000 people will get 15,000 identical answers. So that's really what I'm going to expect. Okay, so let's talk about the population here. There are not 4 people in this planet. No, it's 4.626 million. All right. Estimate when the population will reach 4 million using your graphing calculator. Okay, why don't we go ahead and do that? So we're going to do this on our graphing calculator. So let's go here. I'm actually going to clear this. right? Okay, so let's graph this. So what do we have? We have 6.248 times that number a, right? Guess what? Even here, you can press the same a, and it's saved for you, to the power of x, graph it. All right, so you can't see anything. Why? Because what is our initial value? It's 6.248, right? So these windows are, way too small for us to see anything. So why don't we go over here to this number, and why don't we make that 10? Okay, now there is something there. But now look, X stands for the time, right? Starting at 0, that's 1965, and then we're going like 20, 30, 40, 50 years. So here, I'm just going to make that, let me just leave it at -10. It gives us a little cushion. But here, I'm going to make this 100. Okay, take a look at that. So it says estimate when the population will reach 4 million. If you want it to reach 4 million, let's go to tab. In F2, we're going to type in 4 for 4 million. Enter. Okay, so do you see how there is clearly a intersection there? I'm going to move these away, and I'm going to find that intersection. So let's go ahead and write the equation that we are solving. We want the final amount to be 4 and equal to 6.248 times 0.993 to the power of x. And let's find the intersection. Analyze graph, intersection, lower bound, upper bound, right there. Okay? When will the population reach 4 million? That's the x value. So here, x is 59.3 years. Okay? 59.3 years. And then, you can talk about, decimal values and so on. Now, also when it says when, this is the actual year that it happens. And 59 years after 1965, that's going to be in 2024. Okay, with that, you can go ahead and do your homework. Have a good day, everybody.